All right, so hello, welcome to class Monday, April 20th. Today we're going to start working with some circuits. So this is most of what we're going to be doing until the end of the year. Uh, so looking at circuits. So when we think of what a circuit is, so I have this right here. I have a little battery wrapped in electrical tape hooked up to some wires. The wires go around to this light bulb and then back here. So, first of all, why is this light bulb not lighting up? It's connected to the battery. Wire goes from the battery into the light bulb. It does have a power source. That's what this is, a AA battery right here. But this side isn't connected. So I connect it and the light bulb turns on. I disconnect it and the light bulb turns off. So it's not the wrong ends, it just wasn't connected there. So when we're looking at this, so let's kind of look at what we need for a circuit. Circuit. We're going to need wires. And this is to complete the circuit. And as we saw, what happened there is I didn't have this other end connected. So if it's not completed, this is going to be an open circuit. And then if it is completed, it's going to be a closed circuit. So that was the difference. We needed to close the circuit. So closed circuit is going to be, you have the battery all around, it can go through the resistor. And then we can have an open circuit where the wire is not fully connected. It just goes down here and then the wire isn't connected. So that's like what happened here. And this is kind of counterintuitive that we need a complete path all the way back. To give you kind of an idea of why that's counterintuitive, in the past, like in the 1700s, we had known kind of electricity existed for a while. There have been ways of making simple batteries for like over 1,000 years. But they kind of thought of it as water. They saw the battery and then they were trying to put the charge somewhere. And so they were intentionally isolating these two things and they were trying to pump charge into a thing and store it like water. And that just kept not working. They kept getting frustrated. Why is this not working? Why is this not working? Well, one day, someone accidentally set this down and there was water. And then the water closed the circuit for them and they realized, hey, now there is stuff moving around. And so it really is kind of counterintuitive that in order to let this move, I need to complete the path. I need a complete path for current to flow. So this allows electricity flows. And this is no electrical flow. So it took a mistake to realize that we need an entire path back to our circuit, back to our battery, for any electricity to actually flow. And then once they kind of got there, they realized, hey, we're not trying to put charge somewhere and put it there and keep it there. We're trying to move it around the circuit continuously in a cycle. All right, so wires. Wires are represented with just lines, so we draw lines for wires. The other thing we need is a battery, so I have this AA battery connected here. So wires allow a path for the stuff to flow. Batteries are going to provide energy and voltage. All right, so we're getting to a new thing, voltage. I'm sure everyone in here has heard of voltage. This is a 1.5 volt battery. So voltage, this is going to be the thing that pushes the current, the thing that pushes the charge through the wires. So pushes the charge. And again, back to what's actually moving, we're talking about the electrons actually moving. So this is going to push the electrons through the current. Not through the current, through the wires. All right, so I have a battery that's pushing the charge through the wires. We draw batteries like this, so it's small line, long line like this. Or you could have more lines like long, short, long, short. So a battery is going to be a symbol like either of those. So this is that push, the thing pushing the thing through the wires, pushing the charge through the wires. And then we have the thing that's actually using the energy. So that's going to be my light bulb right here. And in general, this is just going to be what's called a resistor. So a resistor is going to use up that energy / voltage to do useful work. So anything that we plug in is going to be a resistor. So I plug in a light bulb, that's my resistor. You turn on a light switch, the light is resistor. You plug in a refrigerator, the refrigerator is a resistor. So resistors are going to be using up that energy to do useful work. Or sometimes it's just going to still the energy and turn it into heat and just kind of waste it. So there's reasons for using resistors other than these useful things. So I have this circuit, so the resistor is using up the energy, and resistor is going to be a squiggly line kind of like that. So pretty much anything I plug into a circuit, I'm just going to draw it as a squiggly line as a resistor. All right, so wires are going to carry the current, so carry the charge. And then that moving charge is going to be current. Current is our moving charge. So the wire carries the charge around. The battery is going to push the charge or push the current. And then our resistor is going to use that up. It's going to resist the current. So there's a good graphic that I meant to look up and then Kali posted. So that was good because I forgot to actually look this up. But yeah, this is everything kind of in a nutshell. So I have the voltage. The battery provides a voltage that's trying to push the charge through the circuit. Amps, this is our current. Our current is trying to move through the circuit. So these are the electrons trying to actually move through the wire itself. So I have the current moving through the circuit. And then I have my resistor up here that's trying to slow the current down. So battery pushes the current. Current is the charge moving through the wire. And resistors are slowing down the current. So we have our equation that's going to relate all of these together. Is called Ohm's law. So Ohm's law is going to be voltage is equal to current times resistance. So V is our voltage. Now, I is the one letter here that's kind of different. So I is our current. There's a few reasons that I is current. One of them is we would want to use the letter C, but the problem with using the letter C is that C is used for constants usually, so we can't really use the letter C, and so we ended up using I. Also, Ampere. I don't know the words they actually use. He was French. A lot of this happened in France. So I don't know what the letter I is derived from, but I think it's something to do with a French word. Sorry, I don't speak French. And then R is going to be our resistance. So the voltage required is going to be the current sent through the circuit times the resistance in that circuit. And so, kind of writing this out. So voltage, units are volts. The symbol is going to be V. So voltage and V. And then the units are V. So this one is nice. The units are going to be the same as the symbol. And the equation is also going to be a V. So voltage provides the push through the circuit. Then we have current. And these are going to be in amps. So ampere, amps. So the symbol is going to be an A for the unit in amps, but the symbol is an I. So in our equation, it's going to be I for current, but A is going to be our unit. So we could say voltage is 5 volts, but our current is going to be, say, 1 amp. And then lastly, we have resistance. So resistance is going to be in ohms. So all these are people: volta, ampere, ohm. Ohm, obviously the same person from Ohm's law. It's AI. What do you? Oh, artificial intelligence. I guess it is AI. Never seen that. So the units, we would use O, but obviously we can't use O for anything. O looks way too much like a 0. So instead of O, we're going to use a capital omega, right? It looks like an O, but it's obviously not a 0. So we use omega. The symbol for resistance, just a capital R. So V equals IR, voltage equals current times resistance. And so we could say resistance is, say, 5 ohms. All right. And then we can define a few things. So defining our current. So current has a little bit more going on. Current is that moving charge through the wires. So current is that moving charge through the wires. So current is also going to be defined as the amount of charge moving through the wire per time. So current is how much charge is moving through the wire per time, or current is going to be charge. Current units are amps, so 1 amp is going to be 1 unit of charge, so 1 coulomb per time per second. So 1 amp is going to be 1 coulomb per second. All right, so we have 3 new units we're kind of dealing with. Yeah, that is a rooster. So I have 2 neighbors with roosters, and I think they crow at each other. I can shut the window if it's too distracting, but yeah, and then they would, like, the chickens wander through the backyard, and then the cat, like, runs around the house following them. I don't know why he does. He's kind of a puny little cat. He'd get completely messed up by any chicken, but I guess he enjoys thinking he could actually hunt a chicken. All right, and then the last little bit is we're talking about things like energy, right? This battery has a bunch of stored energy. That stored energy can be turned into light energy by connecting it to a light bulb. So the other thing that we've already talked about energy. Well, and if we have energy, we can talk about an amount of energy used per time. So that means we can also talk about power is the amount of energy used per time. And we can also look at power for a circuit. So we have a new equation here. So power for a circuit is going to be the amount of current times the voltage for that circuit. So this is the other new equation to kind of go along with Ohm's law. Voltage is current times resistance. Now, we can get power in terms of any two of these variables. I have power as current times voltage, but I know voltage is current times resistance, so I could also write power is equal to current times, well, voltage equals current times resistance. So instead of voltage, I could write IR, right? Because this whole thing is equal to voltage. So current times current. So I could also see power is current squared times resistance. Or I could do power, again, current times voltage. Well, I could solve for current. I know current is going to be voltage divided by resistance. So instead of current, I can write voltage divided by resistance times voltage. So I could also see power is voltage times voltage, voltage squared divided by resistance. So these are going to be useful for other things we do in here. So I can get power for the circuit in terms of any two of the quantities from Ohm's law. All right, so I know I've kind of gone through this fast. We'll kind of show how these work at different points. And if you have questions, please also ask them now, or you can ask them in tutorials tomorrow or next class. We're going to spend a little bit of time on the classwork. I don't think we're going to get through too much of it today. So let's just look at this first problem that I have here. So problem number 1 on the classwork. So I have a circuit here, very similar to this one. Again, we have a battery, which is a 9-volt battery, unlike this one. So I have a 9-volt battery connected to some wires. Now, when we use wires in here, we're always going to assume these are perfect wires without resistance. So I have 0.1, 0.2. Then we go through a resistor down here. Now I have a 3 kilo ohm resistor. Then we go through wires, we get to 0.3, and we get to 0.4 down here. When does the classwork due? I mean, I think I posted it due as next Monday. We're not going to go through it all today, partly because I just want some things to be able to sink in. But yeah, I'm going to end up doing all of the classwork, and then the homework will be you'll be working on your own. All right, so I have all the essential things for a circuit. I have a battery, so I have a voltage source. I have wires that allow current to flow. It goes from one side of the battery all the way back. So both ends of my battery are connected to the circuit. I have a full, complete circuit path for things to flow. And then I have a resistor. Again, the resistor is just the useful thing in the circuit. So most of the time it's going to be something like a light bulb, but just pretty much anything you plug in is resistor. Where is the classwork? The classwork should be under this assignment. So you have the Monday classwork, and the assignment should just be right here, the classwork. The numbers are different. Are you on the homework? Because there's the homework right here, which looks very similar. Yeah, there's two. So they're slightly different. So yeah, the homework is very similar, but slightly different. So right now we're looking at the Monday 420 classwork. So simple circuits classwork is what we're looking at right now. Yeah, simple circuits classwork. Yeah, they look similar on purpose because they are very similar. So yeah, these are going to be two separate grades. So this will be like an entire week's of worth of grades as these two assignments. Right, because I can give you two assignments per week. All right, so I have two values here. So I know my voltage is 9 volts. My resistance is 3 kilo ohms. Well, I can't leave this in kilo ohms. I want everything in base units, right? Meters, kilograms, seconds. I want everything in volts, amps, ohms. Well, this is kilo ohms. Kilo is 1,000, so 3 kilo ohms is 3,000 ohms. There. I want you to write the formula so it's just obvious you're doing work, because some of these are real straightforward. But if you just write answers, it looks like it's copied. I'm pretty sure you're not copying, but I have to hold everyone to the same standard, so I can't just say, oh, I know you normally do your work, but I didn't see any work, so I'm not going to count points off. So in order to have a standard, I want you to show your steps and your work. So A wants to know how much current is in the circuit. Well, I have voltage and resistance, so I'm probably using Ohm's law. Voltage equals current times resistance. Well, I'm trying to figure out how much current goes to the circuit, so we'll solve for current, divide resistance over. Current is voltage divided by resistance. So I have a 9-volt battery sending current through a 3,000 ohm resistor. My calculator is 9 divided by 3,000. So 0.003. 003. The units for current are amps. And I could go through and put this into, if I multiply this by 1,000, I have 3. Well, 3, this is a really small number, so not kiloamps, but milliamps. So I could also put this into milliamps. And my paper tore. So current could also be written as 3 milliamps. And again, just like your last quiz, this test is going to have a decent number of unit conversions. You can leave it as amps, yes. But just kind of showing you if you get small numbers, it might be useful to convert this. Yeah, an amp is a volt per ohm. Yeah, except instead of, oh, you use omega, which that equation shows A equals V divided by O, makes it really look like you're dividing by 0. When we get down to it, the only base unit we have are meters, kilograms, seconds, and volts. Yeah, I know you don't. But I just thought that was a good time to show why we don't use O. But yeah, so meters, kilograms, seconds, and coulombs. So we'd really need to reduce these down to their units. So you could express current in terms of amps per second, volts. I don't want to get too much into that, but you can express volts in terms of coulombs and C equals QV. Yeah, coulombs and volts, and so yeah, you can express these all in terms of different values. Volts, you can express it in terms of base units of kilograms, meters, and seconds. We're not going to get into that. All right. B wants us to figure out how much power does the appliance use. So power is current times voltage. All right, well, current, I got 0.003 amps of current, and I provided 9 volts. So power provided, 9 times 3 is 27, so 0.027, and then power, so watts. Or again, I can put this into, if I multiply this by 1,000, 27 milliwatts. You don't have to convert it. Obviously, you can just leave it in watts. And we can check our other equations that we derived here. There's going to be other times where it's way more useful to use these two equations. So when I set this up, all I know immediately, I'm given my voltage and resistance. So it might have been nice just to go to this equation. Power is voltage squared divided by resistance. So power is voltage squared divided by resistance. I provided 9 volts. So 9 volts squared divided by resistance of 3,000 ohms. 9 squared divided by 3,000. Again, we get 0.027 watts. So that would have been a nice thing to use because voltage squared divided by resistance, not high enough. So voltage squared divided by resistance, I know voltage, I know resistance, so I can get power without even having to do part A. Then we might as well test out our last equation. Power is current squared times resistance. There might be a time where you're given current and resistance, and if you use this equation, we won't have to go calculate the other values. So current, we got that 0.003 amps squared. We have a 3,000 ohm resistor. 0.003 squared times 3,000. And we get the exact same number again. There we go. You can kind of see that now. 0.027 watts. And I'm going to say these equations, it's going to get really useful to know which one of these to use whenever we get to series and parallel circuits. All right, and then finally, C wants us to get the voltage at points 1, 2, 3, and 4. So now, there's a few ways we can talk about voltage. So I can say voltage at a point, or I could say voltage drop from one point to another point. So we can talk about voltage at a point or how much the voltage changes between 2 points. Now, I'm not going to get too in-depth about this, but voltage, another way you can talk about voltage is by calling it a potential. So the word we see potential with a lot that we've seen in this class before was with potential energy. Now, this is really similar to potential energy, but not exactly the same. So potential energy, let's say gravitational potential energy, if I lift something up, that object has gravitational potential energy. It has energy where if I drop it, it will move. Now, charges can have potential energy, right? Inside this battery, there's potential energy. It's the chemical potential energy. If I let the energy move, the light bulb turns on, and that energy is moved, so it gives the charge kinetic energy, and that energy is used up in my light bulb here. So we do have potential energy stored in a battery, but when we're talking about just potential, that's the potential to make something move. So that's saying it doesn't even matter if I have the mass here. If I have this mass here, it has potential energy. But if I just look at this point up here without a mass, it has a potential, and if I put the mass here, it has potential energy. So that's the same thing with this charge. So this battery has a potential, so even without charges, it has a potential to move the charges, and if I put the charge there, it will move. So kind of like potential energy, but a little bit different. If you think of it in that same way for this class, it won't hurt you too much. All right, so potential. So to add voltage, things that are going to add voltage are going to be like batteries. There's other ways of adding voltage. You don't have to have a battery. You could have an electrical generator, batteries, electrical generator. Other things like that. And then things that remove voltage are going to be resistors. And we use resistors really vaguely in here. So like resistor is just this catch-all for anything that uses up the voltage. So resistors are using up my voltage. All right. So for this case, it's going to be my battery that removes voltages. Now we're going to assume we have all perfect wires. So we're going to assume perfect wires with no resistance. And on the small scale, this is a pretty good approximation. So when we're dealing with something like this, our wires here are really short. They're going to have really small resistances compared to, say, the light bulb itself. And I can actually go through and prove this to you. Come on. There we go. Gonna work now. All right, so I can look at, say, across this light bulb. I actually don't know the resistance value for this light bulb, but we'll find out. So this light bulb has a 0.8 ohm resistance, 0.7 ohm resistance. And this wire itself is going to be much smaller. It's going to be, what's showing 0.2, 0.5, yeah, 0.3, there we go. So 0.3 ohm resistor compared to 0.7, 0.8. And this is a really low resistance object. A lot of times we're dealing with a lot larger resistances. So we're just going to assume these wires don't have any resistance, which is going to be an okay approximation, especially when you get to larger and larger resistances. So looking at my circuit right here, I can go through and label these points. So I go through, I have the positive side of the battery here, the negative side. So I have 9 volts. So how much voltage do I have at 0.1? Like, give something 9 volts. How many volts does it have? 9 volts. Now I go through a wire. The wire doesn't use up any of my resistance. So I have 9 volts here. No, we never actually calculated it, but let's see how much voltage this resistor uses up. Well, so voltage, or change in voltage, the amount of voltage this resistor uses, is going to be current times resistance. Well, I have a 0.003 amp current times a 3,000 ohm resistance. So my voltage drop here, my change in voltage, is going to be 9 volts. And particularly, we're using up this voltage, so minus 9 volts. So we lose 9 volts across here. We lose 9 volts here. So how much voltage do I have once I get to 0.3? 0. So I use up all my voltage here. Again, I go across a resistor or a wire, so my voltage isn't going to change, so I still have 0 volts here. So I end up with 0 volts, and then I go back to the battery and I add the 9 volts to this again, right? So this is kind of an endless cycle. I add 9 volts, I use up the 9 volts in the resistor, go back down to 0, 0, and then I go back up to 9 volts when I add it in the battery. And then I use up all 9 volts, go back to 0 volts. Now, this is going to be, it does always end up that nicely. You do always end up, now, this isn't technically always 0 volts. Again, just like potential energy, I can call my height 0 anywhere. So we normally calibrate this point and we call this 0 volts. But whatever value we call this, wherever we call our 0, we always return back to the 0. And it, well, I mean, for this one, if we have a 9 volt battery, if I replace this with a 5 volt battery, if I pull this 9 volt battery out and say I put 5 volts here, it'd go to 5 volts down to 0. And it's really important it goes down to 0 volts due to conservation of energy. Let's imagine a case like we have this battery. Let's say we have a 5 volt battery. We go through, we have this resistor we have here. So this resistor uses up 5 volts. So let's say it doesn't use up all the 5 volts. Let's say this resistor only uses up 3 volts. Volts can be negative, yes. You can have a negative voltage. And it's all relative to where you call your 0. So this whole math would work if I call this point 0, 0, -9, -9, 0. It will still work just fine. Yeah. So if I have this 5 volts, -3 volts, so I go up here, I end up with 5 volts. But let's say I only use up 3 volts. Then I have 2 volts here. All right, well, then I go to the battery and I add 5 volts there. Okay, so I have 7 volts now. 7 volts, this only uses up 3 of those, so now I'm down to 4 volts. Well, I have 4 volts, then I add 5 volts, then I'm up to 9 volts. And then I use 3 of those, so I go down to 6 volts. Then I add 5 volts, so I go up to 11 volts. We get a problem here where this voltage is just continuously increasing and increasing and increasing, and we keep getting an infinite amount of energy. So it's always going to work out where we always use up that same potential. We always get back to that same point. Otherwise, we're just going to be continuously adding energy. So it's not your voltage that's going to change. And in fact, what we're going to see is, thanks to our Ohm's law, our voltage equals current times resistance. What's going to happen is this is always going to change in order to make sure we keep using up all our voltage. So let's say I increase my voltage source. Well, my current is going to go up with my resistance the same. So as my current goes up, I use up more of my voltage. Or if I decrease my voltage, I put in a smaller battery, my voltage goes down, my current is going to drop in a perfect way in order for the resistor to use up all my voltage. So it's going to be the current is going to adjust. We're going to see as we change the battery in here, our current is always going to adjust in such a way that all of my voltage gets used up. And this is just purely due to conservation of energy, that we're not going to be just continuously adding more and more energy to this thing. So see once our voltage at all the different points. So I could say voltage at point 1, well, I've added that 9-volt battery. Voltage at 2, we haven't gone through a resistor yet, so we're still at 9 volts. Then I go through my resistor. My resistor uses up all the voltage. So voltage at point 3, I've used all that up. I've gone down to 0 volts. No resistor here. 4, I'm down to 0 volts. We are just going to always call this 0 volts when I return to my battery in this class. So you can call this negative. You don't have to call that 0. But yeah, we're pretty much always just going to put our 0 when we return to our battery. Just like whenever we do something in class, we're going to call the 0 the floor. 0 height is the floor. It just makes the most sense. And so I could look at these. So if I call 0 volts my floor, my lowest when I return to my battery, I could also get change in voltage across the battery. Well, the battery is going to add 9 volts to the circuit. And then my resistor is going to take those 9 volts away. So change in voltage across the resistor is going to be negative 9 volts. So normally when we're talking about a voltage, if I say my battery has a voltage, so this battery I have right here is a 1.5 volt battery, I'm not really saying what the voltage is at a point. I'm saying the change in voltage across the battery. So the delta V, the change in voltage across this battery is 1.5 volts. This battery adds 1.5 volts to the circuit, and the light bulb uses up the 1.5 volts. And then it returns with 0. So just a little bit more time. I don't want to go over an hour for this class. So that leads us to kind of a little bit more notes, the kind of difference between things in a circuit. So voltage gets added by a battery, goes to the circuit, gets used up by a resistor, and ends back up at 0. So when we're talking about a circuit, so we have voltage added by a battery, then used up by the resistors. And we should probably be a little bit more specific here. It's not just a little used up, and it's completely used up. So all the voltage I send out from the battery gets completely used up. And we can say this in terms of energy also. The energy that the battery puts out is used up by the light bulb. And in a real circuit, some of the energy gets used up in the wires. In reality, some of the voltage is getting used up in the wires here. But then we have the other thing, current. Is current getting used up? What is current? Current is that moving charge, and specifically the moving electrons. No, there's more. There's quite a bit more. We'll keep talking about this next class. We have to go between the difference between series and parallel circuits. So you should be able to do number 1 on the homework. But yeah, the plan was never to get very far on this. I'm trying not to put out a lot of material at once, especially with you trying to learn this all online. So current is that moving charge or electrons. Now, electrons, these are matter and they have this physical charge. Like these are actual things. Are the electrons themselves getting used up? Yeah, you can't complete the homework today unless you have pre-existing knowledge. So I can use up the voltage, I can use up the energy of the electrons, but the electrons themselves aren't getting used up, right? The electrons aren't being created or destroyed, right? So electrons are not created or destroyed. And again, if we want to get really specific, you can create or destroy electrons. It just requires a ridiculous amount of energies. So we're talking about no black hole / particle accelerator. And notice I didn't say atomic bombs. Even atomic bombs are kind of on the low end of the energy scale when we're talking about this. So atomic bombs don't really destroy electrons. Maybe a few of them, but not a lot. So when we're talking about creating or destroying electrons, we're saying atomic bombs are a bit too weak to do this consistently. So if atomic bombs don't consistently destroy or create electrons, then we're definitely not talking about creating or destroying electrons with this tiny little AA battery right here. So moving electrons, these electrons aren't being created or destroyed with these really low energy things. So that means the current isn't getting used up. So the current is not used up. So when I see this, when I have my circuit right here, let's do the same circuit we had before. When I have this 9-volt battery right here, and then my 3000 ohm resistor, I'm sending out a current. Have fun in English. I send out my current, I send out my current equals 0.003 amps. So I have 0.003 coulombs of charge per second. Well, it goes through here. There's still 0.003 amps. Current is those moving electrons. Electrons aren't being created or destroyed, so I have the same number of electrons going through there. Through my resistor, well, electrons aren't being destroyed, so I still have all the electrons moving, so I have the same current going through here. Still haven't created or destroyed electrons, so still 0.003 amps going through here. 0.003 amps going here. And then this battery isn't powerful enough to create or destroy electrons, so all the electrons have to go through here. So all 0.003 amps of current are going through here. So a little bit of a difference between voltage and current. So voltage potential, you can think of voltage like energy. So voltage is not energy, but it's like energy. So this is talking about how much potential each electron has. So the electron, so I could write. So this is like energy of the electrons. Not exactly. So you can think of it like that. So like the energy of the electron. So I can use up voltage because it's similar to the amount of energy in electrons. It's actually directly related to the amount of energy in electrons. So as I use up the electron energy, my voltage is dropping. But my current is the moving charges. I don't actually create or destroy those charges, so my current has to stay constant throughout all of the points. So a little bit of a difference between these. We use up voltage as we go through the circuit and we add it back. We are not using up our current. So that's about all. I don't want to start getting into series and parallel circuits till next class. So again, like you saw, you can't really do much of the homework or classwork. You could do number one of the homework, but we'll get much more into series and parallel circuits next class. So any last minute questions before I go? So yeah, just a few things. We'll keep working on this next class, and in all honesty, we'll probably also keep working on this class after that. So there's the due date on those. Don't stress as much about those. I might move that due date around. But yeah, other things that are kind of been due, you have your Coulomb's law quiz. Make sure you finish that and get that turned in. I've started grading those. You have your test over waves. If you still haven't done that, please do that and get that in. And then labs, get those finished and turned in. Both the homework and classwork are going to be counting as grades on the next week's grade. So I am going to take up both of these assignments, but we are going to go through the entirety of the classwork next. But yeah, we'll keep going through these. As you look through this, if you have questions, please kind of formulate those and then ask them either in tutorials tomorrow or in class next class, and I'll keep going through more of these. Other than that, have a good Monday and try not to be too stressed out with all this online work, and enjoy life being able to work from home.